Everyone, and thank you for joining us today. My name is Jay Singh, and I will be moderating today for the NASA Technology Transfer Program webinar on patented NASA Ames IT and software technologies. Thank you to Sean Sullivan for hosting this webinar, and thank you for everyone who took time out of their schedules to attend. Our panelists today will be Kim Hines, who is the Technology Transfer Office Chief at NASA Ames, Min Yu, who will be speaking about the flexible engine for fast time evolution of flight environments, David Murakami, who will be speaking about the space traffic management architecture technology, Dave Iverson, who will be speaking on the inductive monitoring system, Kenji Kato, who will be speaking about a reconfigurable image generator and database generation system, Jetan Kulkarni, who will be speaking about on the enhancing fault isolation and detection for electric powertrains of UVAs. And following the presentations, I will be giving a short presentation on how to license NASA technology. So at this point, I would like to hand it over to Min.
Hi everyone, I'm Ming-Xue, and I'm the tech lead of extensible traffic management sub-project. In this sub-project, we try to learn the traffic management, to study the traffic management system for all the new entrant vehicles, including small UAVs, up-classy HAL fixed-wing aircraft, HAL balloon, HAL airship, etc. So today I'm going to talk about the technology, the simulator we developed since UTM back to 2017. So we developed this. Sorry, I cannot see the slide. Yeah, we developed this. We call it FE-Cube traffic simulator. It stands for Flexible Engine for Fast Time Evaluation of Flying Environments. Yeah, second slide. Thank you. Yeah, so we know there are a lot of in order to study the traffic system. So we develop traffic simulators. There are a lot of simulators developed back to area when people study the aviation traffic. So usually you have to compromise between fidelity and the computation time. Most of the time you have a very high fidelity, try to incorporate all the critical components in the traffic management system, but usually the runtime is expensive. You can only run very limited number of scenarios. So, or on the other end, in order to have a fast computation time, you kind of throw away a lot of important components. So there are a compromise between these. While when we're developing this traffic simulator, try to achieve, while maintaining the core, fidelity, core functions inside within any traffic management system, we want to push the limit, try to achieve a high computation performance. In order to do that, it's not that easy. Of course, the first step is we utilize the most advanced cutting-edge kind of a GPU processing technology, so we can parallelize that. But that's far from enough to achieve like a Monte Carlo simulation capability, while we incorporated the core functionality within any traffic management system. From the block diagram on the left side, you can see we incorporated most of the critical components in the traffic management system, like scheduling, departure arrival scheduling, conflict management, etc. Of course, we have vehicle dynamics, communication, navigation, those kind of performance. But incorporating that using GPU is not enough to achieve any Monte Carlo simulation capabilities. So beyond of that, we also try to generalize the structure of those critical models like conflict management model. With that kind of generalization, we're able to achieve very fast communication performance while studying the entire system, statistically. So that's a key kind of feature of technology innovation in this kind of a simulator. So we can do with that modularization, with the GPU cloud implementation, we can achieve from anywhere from 1,000 to 100,000x kind of running factors to study the performance of a given traffic system. So next slide, please. So yeah, here we in the past many years we already use that for a lot of applications. Of course, for us we use for a lot of studies and researchers like assess of airborne risk when you have a lot of drones flying in the area, given the wind condition, uncertainty, given the your navigation, performance or uncertainties. How do you assess the probability they're going to conflict with each other, right? So that's kind of thing very important. Also, if you have when we develop a conflict management models, we want to use that to validate how well your conflict management model can perform under what kind of assumptions. Those are all the studies applications we can apply this kind of a simulator to, and also help us define a subsystem requirement. Let's say you have avionics system, you have a navigation system. So to what level then the conformance the conflict management model can perform the best, right? So you want to study the trade-off between what if your position area is large, then how well or how bad the traffic management system can handle. So we also used these are the past sample studies we can apply this simulator towards. So the potential users, of course, like vehicle operators, you can every time, because when you fly a drone, flying a calm day without any wind, or flying a windy day, flying in a windy day, or flying in the city, all these days, you have the same drone, but the risk is different. So every day when you can use that to assess your flight plan, to see if you need to adjust your flight plans such that you have a lower risk, ground risk, and airborne risk, right? And also for insurance company, we did have a kind of a chat with some of the insurance company. We asked them, how do we distinguish, what if we operate a drone in a calm wind day versus a windy day? They say they don't. So that's, there's a lot of room to improve to make it a more accurate assessment for each operations. So, and a service provider, of course, right now majority is for researchers also. So it's like researchers can use that to refine the conflict management models that they're developing, and also to inform what kind of a navigation, navigation control system and avionics kind of accuracy they're targeting. So those are the potential users for this the traffic simulator. Right now, as I mentioned in the previous slide, so this simulator is developed based on implemented on the cloud. So you will have a web access towards that. So anyone is interested, you can can convert it to a software as a service kind of tool for to large and to make it open to wider audience and wider kind of users. I think that's given the time limit, that's all we want to share today. So if you have any question, we do have a lot of kind of detailed information about this traffic simulator, and feel free if you want to have any question. So thank you all. Thanks.
Thank you, Min. That was very interesting. Give me 1 second here. Let me go over the Q&A.
Yeah, I just saw. Should I answer them directly?
Yeah, I can pitch them to you.
Sure.
So yeah, so what is FE3?
Oh, just an short name for flexible engine for fast time evaluation of flight environments. That's just kind of a short name for this is actually low altitude traffic simulator.
Oh, very interesting.
Mm-hmm.
So when you created this, what was kind of the intention for it, as to why this was something that you were working on?
So intention was we lack of this kind of a high computational performance simulator, um, especially for when you consider a lot of uncertainties like wind uncertainty, like communication, navigation, surveillance uncertainties. So uh, we need a Monte Carlo simulation capability for a lot of studies, right? So deriving a requirement, assess the risk, right? So that's kind of a motivation, big motivation when we start to invent this traffic simulator. Existing, as I mentioned, existing simulator either they consider everything, but they're very slow, at least not up to a Monte Carlo simulation capability level. So that's a big motivation behind this.
Okay, very interesting. Um, and what is the hardware slash OS requirement? Can it operate on a containerized environment in the cloud?
Yeah, so right now it's deployed on the AWS Gov Cloud, using auto scale to call the GPU instances. So you can also that's currently cloud deployment, and also within NASA, when we do internal researches, we also use Linux based kind of a server. So as long as with it has GPU inside of the server.
Oh, very interesting. Thank you. Thank you for explaining all that information, and thank you for the presentation.
Thank you.
So next up, we have David, and he'll be talking about space traffic management architecture.
Okay, yeah, thanks a lot. And I'll try to respect everyone's time here. So I'm David Burakami. I've been working on space traffic management for the last couple years, and it's pretty closely related to that XTM and the drone traffic management, UTM, and all of that. And it's kind of seeing what we could take from UTM and its successes and its architecture and applying it to this new problem of space traffic management. So I presume that this is kind of a niche topic. So probably most people have heard of space debris, but there's a lot more to it going on right now that makes it more and more urgent. I'll describe a bit of that and then talk about the actual prototype that we've built. So first thing, I've got this little video to illustrate what space debris, what that problem is like. So all of those green specks you see are satellites. So you see the geostationary ring around the Earth here, a whole bunch of spread out spots in between Geo and Leo, and then this big cloud around low Earth orbit. So we're zooming in towards an example of kind of a typical debris object. So this is an intact satellite. It's the Defense Meteorological Satellite Program, 5A-F3, but it's been up there since 1971. And it's going to stay up there for a really long time also. So that's kind of a characteristic of space, right? So that's up there, and it's going to come close to other objects in space every so often. So this is filtering all the objects that it's going to come close to within 24 hours. So that was around 120 objects. And we're going to see what that looks like over one pass over the South Pole. So first conjunction was with a piece of a Chinese weather satellite that was blown up in 2007, I think, an anti-satellite missile test. That one was a bit of an upper stage. That is an active Iridium satellite. And then a piece that comes pretty close of the Iridium Cosmos collision. I think that was 2009 when an Iridium satellite and a dead Russian satellite hit each other and generated a lot of debris. And this is another one with a piece of upper stage, I think, from a rocket. Yeah, and then I think there's one more as we go over South America here. So that is, yeah, another piece of debris from that Iridium Cosmos collision. So that was a half hour. That was 6 close approaches, meaning that the uncertainties you have in position make it kind of possible that they could collide, like 1 in 10,000, at least sort of chance that they could collide. And that's happening continuously all the time. So, right. So just a little bit about the domain. So orbit determination for satellites is hard, right? They're traveling 7 kilometers per second, hundreds of kilometers away. You don't know exactly where they are. So you have to assign kind of a probability cloud to them. And then those clouds will often intersect with each other and give you a non-zero chance of collision. Um, Also, satellites can stay up there for effectively forever if you're in a high sun synchronous orbit or GEO, right? So right now there are about 4,500, I think, active satellites. 25,000 total cataloged objects, which means you can detect it with radar. It means they're bigger than about 10 centimeters. And estimated over 100 million little objects that are around like 1 millimeter size. So there's that. There's also, you've probably heard of Starlink, right? And it's not the only mega constellation that's been proposed. So we're talking like an order of magnitude more congestion, more satellites in space coming up. And there is a new space fence coming up. We'll be able to detect smaller objects. So that means that those things that you couldn't see before, of that 100 million, you could see more of them. So that's just a lot more information to deal with. And also there's a commercial, this used to be all run by the Space Force, but now there are private commercial entities that provide this kind of tracking data. And maybe you've heard of Kessler syndrome, right? Where debris hits other debris, creating more debris. And it just sort of, at some point, space is just really polluted with space debris, and it really affects your satellites. So at the bottom here, is an example of that. So, a space debris impact on Sentinel-1A. So there's this big chunk in the solar array that wasn't there before. And this video here is just a scale of, if you hit any 10 centimeter scale object, it's going to look like this. All that kinetic energy, the huge amounts, turns into an explosion and then fragments everything. So like here, 200,000 fragments produced by this test. So, yeah, and then a little bit about population growth. So that video I showed before, I made 3 years ago. If you noticed, it was 19,000 objects back then. Now it's about 26,000 objects that are tracked. That's like a 30% growth in 3 years. And, it's kind of the age of mega constellations is just getting ramped up here. There's going to be a lot more congestion and a lot more possible collisions happening. And last part of the background is describing the process for deconflicting an active satellite on active satellite conjunction. So this is from a FCC filing between SpaceX and OneWeb. They're constellations that they're competitors, right? So they always you see filings like this every so often, but this describes the process of deconflicting a satellite, a SpaceX satellite that kind of got too close to a OneWeb satellite. And I won't go through all the details, but it's you notice it's emails, right? And then phone calls, and then some technical data being exchanged to engineers, and then evaluating that, and then coming up with more emails, more phone calls, and it's a very manual process. So if you're talking about tens of thousands of satellites in the future, this process really has to be automated if you're going to maintain safety. So that's kind of the background, the problem that we're trying to solve. And then so the actual space traffic management architecture, we kind of started from the UTM project, which was developed for managing drones in low altitude airspace. And there's some commonalities there. So a rapid growth in the number of drones, right? And the type of participants and the complexity of the interactions, like suddenly growing very quickly. And then this decentralized, automated, very scalable architecture that was developed for that domain. So the basic concepts from UTM we apply to space traffic management, and it actually turns out that it's it's actually a fairly good fit. So the most important parts of that are that an open architecture, meaning that the standards and things like that are all open, but also the process of developing them was also open. Um, yes, and then the main thing coming out of that, one of the main things is this ability to perform cooperative management with diverse participants. So there's not, there doesn't need to be one traffic controller for space that has to tell everybody what to do. The idea is that this is community driven, and that's really necessary for space. Like there's no such thing as like an FAA for space, right? It's not sort of it's inherently international, and these kinds of efforts have to be ground up, sort of developed that way. And this providing the technical architecture for data exchange and decision making here goes a long way towards that. So right, so if this is basically a chart of the roles and responsibilities, which are really the highest level, most important part of this architecture. So we define these things called space service suppliers. They are basically intermediaries for the owner operators who run spacecraft, and that's their interface to the rest of the space traffic management network. And then supplemental data suppliers, providing things like space weather information. The conjunction assessment supplier, which does all of the number crunching to identify possible conjunctions and evaluate your mitigations for them. And then space, space surveillance, where you get the tracking information. And so each one of these have defined APIs and defined roles in this network. So, right, that's just basically what the short description that I gave there. So we prototyped this at Ames, a small lab with a couple of people. Just a couple of slides here about some of the details here, but containers running on, in our case, not in the cloud, but on computers in that laboratory. So this is sort of one interface, the S3, the interface that spacecraft operators would communicate with. This is the STM gateway, sort of the part that organizes all of the participants in the network. And then, I won't get too much into this, but deployment diagram for how we put that together in the lab. And last part here is just a sequence diagram for how we would handle that conjunction that I talked about earlier, that SpaceX OneWeb example, setting up screening requests, and if there's a conjunction detected, it goes back to the relevant space service supplier. They propose maneuvers, and then it's evaluated by each of them, and then the results get published. So this is like an automated version of that path that the emails and calls that I described earlier. And right, so last slide here is we built that data infrastructure, I guess we could call it, and then we wanted to use it. We built kind of an application to run on it. So we built an automated maneuver advisor. So if a conjunction is detected, a little piece of software that will advise the spacecraft operator, like here's a list of possible maneuvers you can use to mitigate it. And I won't get into too many of the details, but sort of a compartmentalized way of taking care of that. So screening, developing maneuvers, and then choosing some decision aids for the operator to choose which maneuver to take, and then see propagate it forward in time and see if it causes, if it resolves the problem, if it causes additional conjunctions, that kind of a thing. And that's it. Hopefully I was good on time.
Yeah, that was great. Thank you. That was very interesting. We got a question. How are space debris being tracked and monitored? Is it by ground to space telescope, by low orbit satellite monitor in real time? So how is it tracked?
Yeah, so a couple different ways. So debris which is non-cooperative. That's usually radars on the ground. The U.S. Space Force is the biggest source of data, but now there's Leo Labs, which is a commercial company that provides that kind of service. That's something that's happening right now. Active satellites can have GPS, and so they can actually self-report with a lot of accuracy where they are, what their trajectories are like. And yeah, if you're in geostationary orbit, usually it's telescopes. But yeah, there's a lot of different methods, a lot of different formats, and it's not trivial to, be able to get everyone to talk to each other.
Ah, very interesting. Cool. And does STM as presented in the flowchart exist at this time?
Not real. This stuff is surprisingly chaotic, like when I first came into this, like I thought that there'd be more order to it, but I don't know, it's very ad hoc. So different organizations will have different processes, different procedures, different data formats. But yeah, you have to call, you have to know people, you have to send emails, that kind of a thing. So yeah, it's very ad hoc. I'd say there isn't like a system right now. It's people do what they need to do to get the job done right now, but there really needs to be a system.
And do you think that if someone were to license this technology and kind of go from there, do you think that you can use like this technology as a basis for that system?
That's the hope. Yeah. Yeah. That's definitely the idea there. Sort of we're taking our cues from the development and the way that UTM became successful. So yeah, we're definitely looking for partners, like people who are interested. That's the whole point of this.
Great. And then for the sake of time, I got one last question. What is the theoretical limit to the number, so the order of magnitude of satellites that can be supported at low Earth orbit? If that's something that you can answer.
Right. That's a good question. Um, so this idea of a carrying capacity, like for certain orbits and altitudes, like that comes up every so often, and then maybe you license those, like geo satellites, you get slots, right? You get like this azimuth, this chunk of the sky. Um, I know that there's a group in MIT that is looking at that, but yeah, I don't know too much about that.
Um, then I guess one last question. Can this be used for debris removal?
Yeah, it's necessary part of identifying the debris to be removed. I mean, yeah. So, right. So this is basically just um, get um, making it possible for everybody to talk to each other, like talk the same language and be able to move information around each other seamlessly. And yeah, if you're doing something like, if you're on orbit and navigating, you need up-to-date information. And now you're going to have multiple sources of it, right? That's what do you believe SpaceX over Leo Lab or Space Force over Leo Labs, that kind of a thing. Um, but yeah, in the operational part of a debris removal mission, and also like defining what your target should be, which one has the highest possible impact. Yeah, I think this could be useful.
Awesome. Thank you so much. That was very informative.
Yeah, thanks a lot. Thanks, everyone.
Okay.
Say, Dave Iverson's up next. We'll be talking about inductive monitoring system. I will be sharing his slides for him. Just give me 1 second.
Okay, good morning or afternoon, depending on where you're listening from. Talk about something a little bit different. This is the inductive monitoring system. You can click to the next slide. And what this is a data-driven anomaly detection software that we use for system health monitoring. And that means what it does is watch data collected from your equipment or a system and let you know if it's doing something different than a model of the normal operations on that system. And that normal model that it uses is built using nominal data collected from the system itself. Next, please. So in other words, it automatically learns how the system typically behaves from its own data and lets you know if it's behaving differently now. And one more, please. This one kind of clicks in with a bunch of stuff. You could even go through and click in the list. Like I said, it's a data-driven system. It does have the ability and has been able to detect small problems before they turn into big problems, which is a big thing. We did notice some precursors to problems in archive data, like on the space station, that turned into something bigger that they hadn't noticed. So that's a good demonstration of that. Since you train it on normal data and you don't actually have to go in and encode fault signatures from known faults, it's able to detect unanticipated faults, things that you never thought of. It just compares your system to what they expect for normal operations, which helps with the operator workloads. It monitors multiple parameters all at once and how they interact. So it saves some of the burden from the operators for doing that, helps increase situational awareness, and maintain safe and efficient operations. Applicable, it can be used with most any system that has a data collection capability and fairly consistent operations. It uses that data to automatically build the system models, allowing for rapid and low-cost monitoring system development, which I think is the last bullet on there. I can go on to the next slide. It has two modules, the learning or the modeling module, which is run offline typically. So what that does is it takes archived system data, nominal operations data, from whatever you're trying to monitor. It's grouped into vectors of multiple parameters in each group. And what IMS does is it takes those vectors and forms what we call nominal operating regions, or clusters of, I guess you could call it, nominal regions in the operating space, where you expect that data to fall during the normal operation of the system that you're working with. And that's all put into a call it a knowledge base or a model. That model is then transferred down to the monitoring module, which is a compact system that can run either onboard your vehicle or your other system, or you could analyze archive data offline with that. And what that does is it collects the data, either real time or archived, formats it into those vectors, and then compares it to that nominal model. And the output from that is a deviation score, how far your model has drifted, I guess, from the model in your normal operations. And that's just a number. It says you're close, you're far away, and it also gives you information about which of the parameters are contributing to that, so it can help you with some of the diagnostics along that line. This is not a diagnostic system in itself. It just does the detection, but it's enough to do the monitoring and let you know that there's something going on in case you want to dig into it further. And next, to save you from listening to me for too much longer, there was a video that we put together a while back that's a little bit dated, but still relevant. It illustrates some IMS methods and applications. If we want to save some time, we could even skip it, but I'll let Jay make the call on that. Okay, hope you enjoyed that. I saw a question about applicability to other systems outside of flight systems. I tried to answer it in the chat box, but it wouldn't let me. Yeah, it's IMS. It doesn't care what it's being applied to. It's been used in a lot of different applications outside of flight systems. The power industry has had a lot of use of it. We're looking right now at, we're supporting the Artemis launch, looking at some of the industrial equipment at the launch pad that they're using for the environmental control system. So yeah, if you have a system that collects data and does something fairly consistently. It works whether it flies or not.
That's great. Yeah, thank you for the video and the presentation. It's very informative. We had one question who asked, who do we speak to about bringing systems like this to market? So it'd be us. It would be the Technology Transfer Office, and we can reach out to you after the presentation to see where we can go from there. And we'll just wait for a couple more questions to come in. So what was the initial reason why you created this, or why there was a need for this?
Now, back when we were starting on this, a lot of the advanced monitoring and diagnostics was done. Well, the easy way to do it was to look at different parameters and just set limits on them. But the fancier way to do it was basically to build a simulation or a model to sort of run alongside your system and see if it's doing what it does. But a lot of systems you can't really model. We were working with a rocket engine at the time, so we decided to see if we could do something with automated modeling, just using the data to really make that process a lot easier and more efficient. And that's how we got going, and it took off from there.
Oh, very awesome. And then we have another question about the process of selecting companies. And for everyone who's interested in licensing technology, after the remaining presentations, I'll be going over how to do that and what the process would be for that. Dave, thank you so much. This is very interesting, very informative. It seems like there's people who are interested in commercializing technology. Thank you for the presentation.
My pleasure.
And next up, we have Chetan talking about enhancing fault isolation and detection for electric powertrains of UVAs.
Thanks for the opportunity. So the work what we are going to present today is part of the whole team. So we are 4 of us who have come up with this methodology, and the basically it's applicable to UAVs, but it can be applied to any other complex system. So NASA's system-wide safety project, it's developing innovative data solutions to make sure that there is rapid and repeatable access to transformed national airspace, and the airspace should be kept in the most safest possible manner, such that these vehicles which are at low altitudes, they are going from point A to point B, but in that completion of the mission, they are also keeping the vehicle safe, the airspace safe, as well as anyone on the ground, because since they are very close to the ground, anyone on the ground is safe, especially if it's in a very high dense population of urban area. And these increasing number of electric propulsion systems, they will be entering the airspace, and they will need very high safety standards, because that's one of the key reasons of the low altitude airspace. And a key element which would help in ensuring that the safety is properly maintained is through diagnosis of failure through fault detection and isolation. So first we need to detect where the fault is in the vehicle itself, and then to isolate the fault. So that way we can do a decision based on it. And the group what we are part of is the fault diagnostics and prognostics group. So we first need to know where the fault is there in the system, isolate the fault, and then make a prediction that how that fault is going to propagate or going to affect the system as a whole. And in this case, it would be specifically catered towards how safe the system is going to be. And this applies to any complex systems. The work what we do in our group looks into right from like structures, it looks at actuators. We have done a lot of work on batteries, and then we are looking into this new electric powertrain or electric propulsion systems for UAVs and UAM type of vehicles, which will be coming in the future. So it leverages on a very combination of the FMEA, which is called the failure mode and effect analysis, and Bayesian network. which is trying to create a dependability structure within the diagnostics framework and mapping the failure events from FMEA within the using a Bayesian network. And this is some of the novelty of the work, what we are trying to make sure that whatever the prior information is available, it could be the schematic diagram of a complex system, what are the failure hazard analysis, or what's that prior work which has been done. Once you have that structure laid out, and that comes in the development phase of the system itself, and then how can you implement a qualitative or a quantitative Bayesian framework under it. So that's the combination of work what we have done is using prior information and then applying a Bayesian framework to it. So what happens is you have each node in the network, which is represented either by the fault, a failure mode, or a root cause and an effect. And then there is a causal relationship between the two elements or these nodes, which actually gives you a fault, first of all detection, and then as you climb up in the node or as you climb up in the chain, you are able to then isolate the fault. So you are able to exactly detect where the fault is. And this is done for any complex system. So you can have a very complex system. The example what we have taken is a powertrain, because that's something one of the needs for today's work or in the project under SWS. But you can take up any complex system, you can break down the system, and you can have a system being demonstrating that where the fault is and how can you take care of or do a decision based on those faults. So what we're trying to do is first identify and quantify what are the effects, and then identify the hazards, what is the severity, and what are the probability effects. So next comes is based on the type of fault which is seen, what is the probability that if you see effect 1, there could be a fault of failure mode 1, and whose root cause could be cause 1 or cause 2. So that is the Bayesian framework comes into picture, where then you are trying to identify based on what is the probability of failure or the probability of cause 1 occurring as opposed to cause 2 occurring, which lead to the same effect. And for that, we need to know in more depth what the system is, and that's through the system physics models what we develop. We have a capability that you can develop this system physics models, and those could be based on the first principles, those could be based on data-driven methods. There's a new way or a hybrid approach where you are combining data-driven approaches and physics-based models. So there could be any number of different options which are available, and you could combine those options to get you what is the cause or what could be the root cause of it. As an example, what we have demonstrated that is you could, when a UAV or a UAM vehicle is flying, you could have multiple complex systems in the same vehicle where you have avionics, you have structures, composites, you have different actuator systems, and then you have the powertrain. So these all systems are working in tandem, and they have their own cascading effects on each other. So what we did was then we isolated a subsystem under it, which was the power system. And in the power system, if you observe that the blue ones are everything is the battery. So the power system consists of your battery pack. So you have multiple lithium ion or lithium polymer type of batteries. You have your speed controllers, and then you have your motors. So those are the asynchronous or the synchronous motors. So the blue one are all faults or sensor information for the batteries. The red one is for the motors, and then the yellow or the green ones, what you see, that's the speed controllers or the PWM speed controllers, which could be MOSFETs or any other switching circuits. And whenever we are trying to look into these systems, so for example, if you look at TBs, those are temperatures, IBs are the currents, and then VB is the voltage. And then similarly for the motors and for the speed controllers, you have their respective voltages and temperatures. So these are all the sensor information which is being fed to the tool. And for example, if you see a variation in the VB, which is the voltage V or the voltage part, so that could be triggered, an anomalous voltage reading VB could be triggered by either VE, which is due to the speed controller, or the motor, which is the voltage on the motor. So if we have this, we have the same anomalous fault readings on the three sensors, or due to these three sensor values, what would be the probability that there is a failure in either the motor or the battery or the speed controller? And then the tool, based on its prior information and also the underlying physics models for each of those systems, it's able to give you the user or the system an output where it ranks the probability of failure. So based on the information what we have for the sensors, the probability of failure, the SOC, which is the state of charge of the motor, has the highest probability. So that's why it has a probability of close to 0.8, while the state of health, which is basically the battery aging, that has a low probability below that. And then the motor winding, which is the M wind, that has the least probability. So these are the top three probabilities that these three systems could be, or these three could be the root causes. And that information is then fed to the prognoser, which is able to then, if the state of charge is the fault, the prognostic algorithm is invoked, and the prognostic algorithm can give you an estimate that based on the magnitude of the fault, how much time is left. So is there 10 minutes for the system needs the battery before the battery would discharge completely, or do we have 20 minutes and the pilot or the autopilot, depending on what the system is, they need to take a decision to land the vehicle to the most safest, closest, or the safest vertiport. So this information, in this case, it's very clear that there are three systems, the three high priority faults. All three root causes could invoke a prognoser on themselves, and the combined effect would give an assessment to the decision maker, that could be a pilot or an autonomous system, to either land the vehicle, or based on whatever the prior set requirements are for the vehicle to be in the most safest possible landing zone, or to reach its destination. So what are the applications to this? In the current scenario, we are looking at something for the vehicle systems health management. So we are looking into the different areas of UAVs, and also for aeronautics and space applications, which are mostly related towards autonomy. So wherever we are looking to have a system to run on its own, so this application is the most efficient one, the way we have built it, because first of all, it requires prior information. It's able to get whatever the system information is, it's able to capture that information and then keep on updating that information. The very good thing about this work is that as your system ages, for example, as we see in this schematic, that your avionics systems or your structures or your actuators, as they age, the efficiency of the systems changes because their parameters keep on changing. And that's something what the prognostics work, what we do, is very much capable of adding to it. So your Bayesian networks keeps on changing. So for example, like in the earlier example, if we saw that the priority of the three faults, what was the state of charge, state of health, and the motor winding was 1, 2, 3. As the system ages, if the battery is aging faster, at a faster rate than the motor, the next time, or the vice versa, the next time when you have a fault, probably a motor winding fault would go in a higher probability of failure than a battery fault. And that's the reason behind that is your prior information, what is there, it keeps on updating as the systems age over the period of time. And this is the novelty of the work, where you are able to input the probability of failures being changed at every flight duration, at the end of every flight, or at the end of a couple of flights, depending on how the systems age. So that's the key takeaway from this work, is there is this dynamic update of the failure probabilities, which are able to detect a fault and then isolate the fault. So your fault detection and isolation may keep on changing depending on in what state of health the vehicle is in its lifetime. So in addition to this key applications, we are able to do the prediction and predictive and condition maintenance for complex systems. So any complex systems is very well able to adapt to this framework. Any R&D or prognostics health management for condition-based maintenance where you're developing health management software, the tool is very much capable of adding the system to it. So you are able to make any changes depending on what the system is. So there is good potential for commercial applications. It may be in any of the IoT applications what the users are looking for. So there is the tool is available, the libraries are available, so it's very easy to integrate with any of these other applications. On the benefit side, it's very easy to understand, so we can do a rapid understanding of isolating and informing response based on what the faults are in these complex systems. It's a very scalable architecture, so as we can see from the schematic that though we have an application to just the powertrain, but you can have a complete vehicle being running in the same framework, and we can have different subsystems being isolated based on what the complexity of the subsystem is, or what is the priority or the severity of that complex systems. Ability to have real-time diagnostics. So real-time diagnostics is very much essential, especially when we are running UAV or UAM type of vehicles, because they are so in a low altitude or low altitude urban dense urban areas. So knowing what the health of the system is and what its effects are going to be on the airspace, that's a very key requirement. So having that real-time requirement of providing feedback for safety to the pilot, to the operator, as well as to the airspace is very much a key. And as I mentioned earlier, it incorporates age and usage rate for specifications of components and subsystems. So as the system ages, we are able to take that information. So if the reliability of the system when it was new was probably very high, as the system is going through different stress and conditions or operating conditions, that reliability will go down, and that's when the probability of failure would increase to specific routes also where the vehicle is flying. So this is the update part of incorporating aging and degradation is what prognostics is, and we have been working on this topic for the last as a group for the last more than 15 to 16 years. So this step is the tool provides this very good study what we have done over the last several years. And then it's not overly constrained by a finite set of compliant hardware. So there is no specification of specific hardware to be used. Currently, the package is available as an in Python, but it's also available in C++, as well as if some users are looking into MATLAB, there is a capability of porting it to it. But it's it's not constrained on what the hardware is. It's very much being used or can be shifted from either of the different platforms. So that's the brief overview of the work. We have published several papers on this, and also Jay will have the document what we have prepared for this work. So please access it, and I'll be happy to answer any questions going forward.
Thank you. That was very, very interesting, very informative. As we wait
Thanks.
for questions to trickle in, so it seems like most of it's for I guess like airspace things, things that are in the air. Can you use this for any other application that you need fault isolation detection for electric powertrains for like cars and things like that?
Oh, absolutely. Yes. Yeah. the application or this example was for airspace, but it can be used for powertrain in cars, and it need not be in powertrains. If you have completely different systems, which could be, as I mentioned, like you have an actuator system, you can absolutely use it on that. If you have a composites, like multiple composite systems which are connected to each other, you can use exactly on that. We have used this on pneumatic valves. We have a very similar diagnoser which has been used on pneumatic valves, which is actually being used to fill the fuel in the shuttle. So those valves actually sit at Kennedy Space Center, but we have those valves in the lab, and we have implemented a similar system on those. So it's a very there are different applications. You can think of any complex system application where you have sensor information, and we can deploy the system there.
Oh, very awesome. So with that, is it hard to kind of move over to that type of pneumatic wall, or is it pretty simple if you have kind of a software background?
Yes, actually, if you have a good software background, it is not that difficult because the framework has been developed. The structure is there. Only the requirements are what type of sensors you have. So that in the first slide where I showed the schematic diagram which is required. So I think that would be the key thing. If you know what the system is, what are its inputs and outputs, this system is could be deployed. So it's very easy from that point. Once that first two parts are there, what are the schematic, what if you have any failure analysis being done, that would help in putting the system prior information of the system. Once those things are done, it's deployable.
Fantastic. Thank you. That is very informative.
Sure. Perfect.
Thank you for the presentation.
Sounds good. Thanks a lot. Thanks for the opportunity, Jay.
Of course. And next we have Kenji, who will be talking about the reconfigurable image generator and database generation system.
So my name is Kenji Kato. I'm a principal research engineer, and today I'm going to be talking about the reconfigurable image generation system, or RIG as we like to call it. And really one of the big things about this is why an eye limiting display resolution matters and how to achieve it using this technology. So what does that mean, and what are we talking about? So to give you some background, this project started with a program called the Operationally Based Vision Assessment Program, or OBVA. And the idea was to study human vision systems and create new testing standards for an operationally relevant environment. It means that, we're not just in a visual simulation environment, we're actually trying to achieve what happens in the real world. This was a collaborative effort between NASA Ames and the Air Force Research Labs, or AFRL, and the U.S. Air Force School of Aerospace Medicine. The project was really to create a new kind of simulation system, which is what RIG is, that could create a visual acuity that actually approached the limits of human vision. So on the side here, you actually see a standard vision chart that most of you are probably familiar with when you go to the eye doctor. And that's for testing what's called visual acuity, a resolution of an image. But the other part of that is something called color, of course, right? So there are those that have color blindness who might not be able to see these dot patterns in the numbers, that very similar to something you take when you go to a driving test. But what's interesting is that really most simulation engines up till really recently only really worried about that first point there, and didn't even do that in the way that you need for operationally based or true real world scenarios. Color was also something that is looked at, but not always the color accuracy of a system. But a bigger one is what's called contrast sensitivity. How is the contrast vision of a pilot or individual taken into account when working with a simulation engine? And so here you see a standard gradation going from black to white, black to white, black to white, with different resolutions that goes across this chart. And this is something that simulators have really just started tackling recently. Along with that is what's called dynamic visual acuity, or the update latency. Now, this is known about, but sometimes, again, is not always taken into account when you're building a very complex system. And then there's the operational relevance, or basically kind of the field of view. How big of an area you're looking at. So all these different things are things that we considered as part of our project for OBVA. And what the biggest challenge is that young U.S. Air Force pilots that come into like the Air Force Academy have on average a 2013 visual acuity. What does that mean? Well, most people hear 20/20 and think that's perfect vision. That's not actually true. It's average vision. It's what the average is for most people. The human limits of visual acuity actually go down to about 28. And what that really means is that in a standard vision test, if you have 20/20 vision, it means that standing at 20 feet away, you can read a picture or an image or text. But 2013, which is what the average Air Force pilot has, standing at 20 feet away, the average person would have to stand at 13 feet to see that same image at a crisp clarity. And pilots can go down easily into the 2010, if not near the human perceptual limit of 28. The problem with that is that FAA flight simulators on average have a visual acuity of about 20/60, meaning that they are significantly under that of the standard average visual acuity and well away from what your standard Air Force pilot has to have. So taking all these things into account, how do you build a visual system that takes this image? This is a 2080 image. This is taken using a super high resolution camera several years ago of Times Square. This is what you would see standing on this rooftop with a 2080 visual acuity at best. This, hopefully you can see the differential now, is what you would see with 2010 visual acuity. Notice the crispness, that you can read the text in the distance. You can see all the little details in the image here. You can see the people on the sidewalk, all those things, right? The difference is that now on the left-hand side, you see 2010, and on the right-hand side, you see 2080. So there's a big differential between these. And the problem is that the average flight simulator is between these. It's not at the 2010 visual acuity, but it's not quite at the 2080 anymore, which is where they actually used to be. Now, commercially available systems, the other thing is that they, up till just really recently, have been unable to achieve this kind of visual acuity with their systems. Now, with the advent of newer projection technology, things like that, you can get closer to this now. And when we started this project, really even 4K, let alone 8K projectors were not a thing that not widely distributed yet. Just really Deacon, formerly of Quantum 3D, Gemini Technology, myself. I used to work at Presagius, which is a high-end visualization company, Multigen, Centric, Naval Postgraduate School, and then Nelson EY, who was also at Presagius and Multigen. So we got together with the scientists to build basically a high-end visual system. So to achieve a 2010 visual acuity, we had to design a 150 megapixel simulation environment. At the time, no one had done that. That was an unheard of system at the time. And that means that it had a visual or a pixel ratio of 20,000 by 7,000 pixels in a 4-meter spherical dome. And it had a maximum of 160 horizontal degrees and 60 vertical degrees in the entire visual field of view. It also ran at 6,000 lumens of brightness, which is really important for achieving close to a daytime lighting condition or different lighting differentials that you need. Also had a color space that met or exceeded aviation red, blue, green, and it changed a little bit depending on certain elements in the projection system. And then we ran that, the initial test was at 60 hertz. We then upgraded that to 120 hertz, which we know from our research is kind of the minimum you need for true visual acuity to eliminate these different things that are blurring the vision that can create an after image from a screen, all kinds of different elements. We actually have a couple papers on this. But truly, if you want to get to a high-end visual system, then you have to go to 240 hertz. And there's very few high-end systems that will drop this frame rate. We were able to test some of these early on, and no visualization system can run actually at that 240 hertz visual characteristic to really remove motion blur, things like that. So a little bit about the original project, OBVA simulation facility. It was at Wright Pat Air Force Base in an old centrifuge. But really the key thing is that this was the array of projectors. At the time, you had to have high-end projectors. These were big cinema quality projectors. In the initial implementation, we had 15 of those in a 5x3 grid, and then eventually updated to a 25 projector system. And here in this picture, you can actually see the metal rack system we had to design and build to hold all those projectors. Now, the great thing is that these projection systems, since we did this project originally, have come down in cost as well as size. And so a steel frame rig like this isn't quite as necessary as it was when we first built this system. And one of the big things about this, though, is how we drove it. So the initial driving of this, back when we built the first iteration of the project, we were using one U rack systems that were connected into NVIDIA's first really high-end graphics card called the Quadroplex. That was then networked out into two 4K projectors. So we basically had an 8K projection system running on each of these computers. And then we could project those either vertically or horizontally into the environment, depending on the configuration needs that we needed. So that made basically, if you're thinking of your desktop computer, it was an 8,000 pixel by 2,400 pixel desktop image. Now, the area we had to have for this projected into, we need to get a full visual field of view. So we actually created a dome inside the old centrifuge at Wright Pat Air Force Base that holds all of our images. So in this, you can actually see every one of these primary squares is basically a 4K image, and the ABCD quad, or I should say the ABCD in each of these is a 4K projector into this entire array. And in the end, we were actually able to get 4 images going through a single computer system. So the other part about this is how you synchronize all this. So a lot of us might be familiar with or even have multiple desktops, monitors on our computer, but that's 2 or 3 monitors. Here we're talking about up to 25 projectors in the end that we had to synchronize. And the problem with that is that when you're working across multiple monitors and on your desktop and there's a seam there, you usually won't notice the differentials. But if you're a video game player, you might be playing on a single screen. If you're lucky, you might be playing on a double screen or have a really nice one of these wide monitors. The problem that you see a lot of times is called the visual tearing effect, and that can be caused by the synchronization of the image. Here you can actually see how in this quick example, how the images are ripping apart, and that can happen between the projectors themselves or within the image itself, where you see little tiny lines of jaggedness running through the image. So you have to synchronize all that information. At the time, with the Quadroplex systems we're using, this used NVIDIA's G-Sync 2 system. Again, this can be done with any graphics synchronization, but this is really a clock synchronization mechanism that makes sure that all the drawing of all the images are lockstep put together and make a contiguous image on the screen. So you remember, this is a massive 25 4K projection system that we had to synchronize across all these screens running at 120 hertz. So that's a lot of data. But the thing about that is that it's not necessarily what most people think of as the refresh rate, right? I got 120 hertz TV. Oh, I've got a 240 hertz TV. The bigger problem is what's called latency. And that's actually from the initial input from the user all the way through the computing systems, the drawing mechanism, out to the display system. And that is what is the most critical part. Refresh rate is not latency as well, right? Your standard home theater systems will run at 100 to 500 milliseconds of latency, actually. Even though you have a 120 hertz TV, the latency, or the time between that image coming off your disk or your streaming box to your TV, can be 100 to 500 milliseconds. For good video game systems, it drops into the 80 or even lower now latency between the drawable and the screen itself. But the thing that really we needed for this resolution is we had to achieve below an average of 30 milliseconds. In the rig system, we had between 20 and 56 milliseconds of latency, depending on the control system we used, how the pilot interacted with it. And that means literally from when I move a joystick as a pilot in that cockpit that's sitting in the middle of the dome to the input system, processing of all that input, the reaction time of the visual system, the drawing on there, and then actually having that light go out from the projector and hit the wall is between 20 and 50 milliseconds. So here's just a quick example of some of the things that we used at the time. We were looking at a Sony projector. We looked at a Christie projector. We even tested this against desktop monitors at the time, which 120 hertz were brand new really at the time. And even a classic Trinitron CRT monitor, just to get some classic latency in there. And really, that was really one of the big things, is how do we achieve that? So we came up with a system called RIG, which was our visualization software. It contained two main parts: the IGM, or the manager application, which basically ran the entire simulation. It sets up the configuration of the environment, it loads the simulation, it's what manages the input and output. And then on each of the subsequent systems in the overall configuration, each of these computers running these projectors, we had what's called the IGRs, the RIG renderers. And these are, at the time, a Windows 7 based deployment. We've now hence moved this to Windows 10, 64-bit operating system. And it ran using, at the time, what's called the NVIDIA CNX engine, which was NVIDIA's OpenGL open source engine. It had capability for us to take advantage of direct-to-hardware capabilities, which are very common now, but at the time they were not. And what that means is that you're loading not into the CPU first, but you're loading directly from the load routine into the graphics card, bypassing the CPU and taking full advantage of the GPU. Now, what's crazy about this, though, is that even though this technology is common, there's a lot of engines that still rely upon your CPU to do the drawing or the first pass of the visualization system before handing it off to the GPU. That's why certain video games, for example, look so great, but also cost millions of dollars to make, because they've optimized all those images to load directly into the video card. What we were able to do is kind of bypass that need for an entire visualization team to build that and take advantage of NVIDIA's built-in technology to do this. We also used scalable display technologies to help us do distortion blending, because we were working in a dome structure. We had to make sure that those pixels, if you're in a dome, that the horizon line is perfectly flat. So the horizon that's kind of behind me in my video here, make sure that looks proper. And then we had weather, atmospheric conditions, three-dimensional volumetric clouds. We used a company called Sundog Silver Lining for their atmospheric effects. So this was really taking our in-house homegrown software and then taking some best-of-the-class, off-the-shelf technologies that we could bring together into this solution. The other part of this is we had to build a high-resolution database. Now, most of you are probably familiar with building 3D models and all the things that we can do with AR and VR and simulations. But one of the things we had to have a requirement for this is that we needed real-world data. And a lot of video games and simulations still use what's called synthetically generated terrain or databases, meaning that it's not based on actual photographs and true accurate measurements of the environment. Now, some of you probably have played with the Google Maps 3D capability. In Google Maps 3D, that's all LiDAR data, meaning sampling of the real world. And that's really what we needed to have, is this high fidelity running at a high resolution, high frame rate across a big screen. And so we built a tool called the RIG DBGS, or Database Generation System. And that takes advantage of multiple high resolution data sources from NASA, from the USGS, different agencies. Most of it was open source, and we were able to take that data, pull that information in, and process that into a very high fidelity real world database based on actual imagery versus it being synthetically generated where a modeler has to go out and model a building or things like that. This also utilized some Google Earth capabilities, as well as a company called Presages Creator, which I actually used to work at in the past. their product to take advantage of some of these modeling capabilities as well. So if we needed to add in 3D models, we could do that. And that's where the 3D cultural capability came in. So if we had specific models that were not able to be extracted from the original data, we could add those in using a format called OpenFlight, which is a standard in the simulation community still today, even though it's one of the oldest out there. So the advantage is you can take a lot of access to existing data sets that are in the industry today. And in the end, this is kind of one of the images that we were able to generate. So what you're seeing here is this is an image that actually drew at 2010 visual acuity, meaning that you could see details if you had a 2010 visual acuity, all the little pixels in there. For example, you'll notice that the yellow stripes on the left-hand approach, or even the center approach, those are all from the imagery itself. So in the past, one thing that would happen with most simulation systems is that comes from a hand modeler. We had no hand modeling here. This is all imagery based, meaning it's satellite data or aerial flyover that we've processed into a high fidelity database, but then we maintain the visual resolution of that data, which is hard to do sometimes with image-based data sets, and maintain that up to a 2010 visual acuity, so that as you fly through this environment, you can see all the small details on the airport. You can see that there's aircraft sitting on the airfield on the right-hand side. You can see that there's scuff marks going down the center runway where the approach landing area is and where most pilots hit that landing properly. Right? Here's another shot. Similar to the one that's right behind me in my video. This is showing actually flying a couple of the F-35 Lightnings over the Dallas-Fort Worth area. So this is actually DFW, but here you can see we have volumetric clouds. These are actually clouds that interact and refract light, meaning that as you have that bright side on the left-hand side there where the sun's hitting it, you have a dark side on the right-hand side where it's darkening, and that actually attenuates light through these clouds as the light travels. If the vehicle was to fly through these clouds, you would actually see the clouds. They'd obscure your view, and it would get different densities of that. And then all the surrounding area around DFW. And again, this is all based on aerial flyover and satellite imagery, again, that's been processed into a data set as well. And again, here's another shot of those same aircraft kind of flying over the DFW area. With some, again, lighting characteristics, the terrain information, all this data. And the great thing is that this is, again, running in a 40-foot dome at 120 hertz, right? So this is really pretty much one of the highest end visual acuity systems at the time when we built it that was achievable. So the idea behind RIG is that it's flexible. So while this image was created using technology that at this point is actually almost, I would say, 8 years old, or even 10 years old in some cases, we have been able to take this technology and upgrade it through different visual systems. And that's what the RIG, or the reconfigurable part of the image generation system, is all about. How do you take a visual system and reconfigure it for modern technology? So unfortunately, I can't share any of the new images from some of the simulations we're working on right now. But we are using the technology for things like UAM. We're using it for different space things. We've applied it to different areas as well, beyond the initial visual acuity system that we produced. And that technology lets us, the software lets us to be flexible with the technology. So we can replace the graphics cards. We use next generation NVIDIA cards currently today. We use newer CPUs, we use newer overall operating systems, and we've continued to move the technology forward that allows us to take advantage of what's the state of the art today. And that was the idea behind RIG, is that we didn't have to rewrite the entire visualization system every time new hardware came out, or rewrite an entire section of the software just to make sure that we could really achieve these new goals. So we can swap out the hardware with the software, change parts of the software as needed, and really reconfigure the system as we go along. And really the idea behind RIG was to take advantage of what is best off-the-shelf technology today and move forward with it, while taking advantage of all the learning we had of things of visual acuity, contrast, color, which I really didn't talk about too much here, but the engine will draw up to aviation color spectrum, which means that lights on a runway or things like that are going to draw appropriately, colors to the sky, attenuation in the lighting going through the cloud there. Again, you see now on the left-hand side, the darkness of the cloud, the bright white of the sun hitting the clouds, things like that. Contrast differentials, all these different elements we had to take into account when we built the visualization system. So that's kind of a quick overview of the rig system. If you wanted to get hold of any of us on the team, John Archdeacon, myself, or Nelson Ewai, these are our emails, and you can reach out to us, or you can reach out to the tech transfer group as well. Any questions?
Great, thank you, Kenji. That was really interesting. So as we have questions trickle in, you said you can reconfigure this for a lot of other things. So can you do this for things like cars and whatnot, things like that?
It could be reconfigured for any kind of visual system. That is definitely very achievable. The idea is that, in fact, actually, we looked at several car groups, and actually we had several research transportation companies come and look at this previously. So yeah, it is definitely usable for something like that. I can tell you, and you can go find this research, probably one of the most similar simulators that we know of out there is Lexus has their very large driving simulators, which are beyond just the visual capability of what we do. They also have it on a motion platform, very similar to the VMS simulator we have here at Ames as well. But yes, the technology is definitely applicable to automotive industry.
Great, yeah, thank you. It seems like your presentation was very informative. So thank you so much.
Cool.
And you're still sharing your screen. There you go. And thank you again, everyone, for attending. I will be going over how to license NASA technology, all of the very cool things that you saw today, and how to license those things. Just give me 1 second. Again, thank you everyone for attending, and I'm just going to quickly go over how to license all this NASA technology. Sorry, you can see me right there. There you go. So I'm just going to give you a quick overview of the NASA Technology Transfer Program. We're here in Silicon Valley in Mountain View, California. We have 10 different NASA centers that all have their own technology domains. And for us, as you can see, one of our stronger domains is IT software, UAV, so autonomous vehicles, and reentry systems, and things like health, medicine, biotechnology, things like that. So the NASA Technology Transfer Program has been around since the inception of NASA, and people always wonder, why should a company license NASA technology? And one of the main reasons is it allows a company to access NASA technology for testing, to implement into their system, for a service or a product that could result in sales. And at the end of the day, the Technology Transfer Office cares about the success of commercial businesses and getting the NASA technology out to market. So just two really cool spinoffs that came out of NASA Ames. One is anti-icing formulas that help on airplanes and on train tracks to prevent delays, and a mineral analyzer, which is on the Mars Curiosity rover. What it does is it takes a sample of soil, it shakes it really quickly, and it shoots X-rays through it to get X-ray diffraction. And each mineral has its own signature to it, so you can see what type of mineral that is, or what's in the sample. And that allows you to take a small instrument or smallish instrument out in the field rather than grabbing the soil and then bring it back to a lab and spending time between those things where you can just analyze it in the field itself. And you can learn more about success stories at spinoff.nasa.gov. So to search for technology, you can either go and type it in at the search bar, or you can click on the patent portfolio. So we'll go through the patent portfolio way. And once you click on the patent portfolio, you'll be greeted with the patents, but these are also our 15 categories that we have. Today, we went over IT software, but we have aerospace technologies, sensor technologies, robotics, electrical. things like that. And we have over 1,200 technologies from the 10 different centers available for licensing. And then for today, I'll go through an instrumentation route. So if you click on the instrumentation category, you'll be greeted with technologies in the instrumentation category, and you could either keyword search from there in the search bar, or you can click on the technology. So let's see what happens when we click on the real-time radiation monitoring technology. Once you do that, you'll be greeted with this page. It goes over the technology, the overview of what it does, the benefits, and the applications. And in this instance, with the people who spoke today, you'll see a webinar video right here with the images. If you have any questions on technology, you can click on the questions tab or the questions link, which will send an email to our licensing concierge, and you can ask technical questions and see, what other questions you have about licensing that aren't answered here. If you want to download the PDF of this page to share for like on-the-go things, that's one way to do that. And PDF just kind of shows everything that was on the last page. And the most important part is the patents. When you click on the patent, it's very important to look at the claims and the description of the patent itself, because that's what you'll be licensing. That's what the technology is patented to do, and that's what you'll be licensing, and that's what the use of the technology will be for. And to learn more about just the kind of overall licensing process, you can go to the resources tab and click on how to license. And if you want to license the technology and you read everything up on it, you ask the questions that you need to, you can click on the apply to license that said technology. And one very important thing is you have to be a US formed company to license NASA technology. And so after you click on the how to apply to license technology link, you can go to, you get greeted with this Atlas page, you create a guest account, and then you can go to license type. And there's different license types. There's the evaluation license, which kind of lets you test run a license, or a technology. So you have it for either be 6 months to a year to test out the technology, see if it fits in your portfolio, and there's different fees associated with them, and those get negotiated with you and the licensing manager. But what it does, it allows you to kind of run the technology, see if you need to, if it fits in your portfolio. And the one thing that is very important with the evaluation license is you cannot commercial those technologies. It's just to commercialize technologies. It's just to see if it works for your needs. Then we also have the startup license. So the startup license allows you no upfront costs for commercial use of the technology. So it kind of carves out a competitive marketplace for your technology. And one of the great terms about this is you do not pay any fees on it for the first 3 years or until you make your first sale on the technology. And the startup license also has a so you have to be a startup company to be able to use the startup license. And then you have your commercial license, which is just kind of standard commercial license for companies who want to take NASA technologies and create a commercial product with it. The last few questions in the licensing in the module for your application are right here. Is, U.S.-owned company. How do you tend to use the technology? Things like that. And before you advance to the next section, check the bottom of the page to confirm that your intended license type is listed. And it's very important to complete as much detail as possible because that allows the licensing managers and licensing team to evaluate your technology or your application for the use of your technology. So the stronger your application, the better the licensing team can evaluate the technology, your application. Once you've signed the PDF correctly, your application is submitted and you'll receive a confirmation email that your application has been submitted. And just a quick note on the NASA software catalog. So we have free software at software.nasa.gov. There's different release types for those softwares. You have government purpose, so you need a government contract for that. You have general purpose, which falls under, you can either, some of the technologies you have to be in the US, some are US and foreign, some is just available for the general public. And then you have our open source technology at code.nasa.gov. All but the open source technologies require a software usage agreement. And here are just some quick links for the Technology Transfer Office. You have our main program at technology.nasa.gov, and you can learn how to license it at technology.nasa.gov/license. We also have our success stories at spinoff.nasa.gov. So those are all the companies that have successfully commercialized NASA tech. And then our NASA Home and City, which is a interactive way to see how NASA affects your daily life. And you have myself, and that's my email, jinder.singh@nasa.gov, and then Kim Hines, who is our chief. Her email's there as well. Just one last question for people. It's what is left undone in your company you might search NASA technology for a solution for. Just wanted to say thank you for attending the webinar, and we look forward to any questions or emails you may have after this. Thank you so much.